Okay, so in this video, we're going to look at another plotting package, which has a little bit more power than some of the other plotting packages we've looked at. We've looked at Seaborn and Matplotlib in previous videos, but now we're going to look at Plotly. Now, we're going to do some explorations on the things that we can do with Plotly. A lot of these examples I have taken from the Plotly website themselves. So you can get more information and more examples from the Plotly documentation itself. Now, there's lots of different kinds of graphs that we can make, and there's, of course, standard statistical graphs and graphs which are a little bit more enhanced. One of the nice things about Plotly is that it does also allow you to do things like animations, which are nice. All right, so we're going to import Plotly Express as PX, and then also pandas so that we can work with the data frames. The Gapminder data set is built into Plotly, and this is a common sort of global data set. It has geographic information, it has information about GDP and life expectancy and various other properties that are often used as a demonstration data set for a wide variety of examples. So we're just going to import this data set, and we're going to look at the first 15 lines. And so some of the information that we can see in this data set is we have country names, we have the continent they live on, the year, so this is up in 5-year increments. So we have Afghanistan in Asia, we have some countries in Europe, we have all over the world. We have life expectancy, population, GDP, and then some abbreviations for different information about the country and which continent they're on and so forth. So this is the kind of data that we have. We're going to definitely be able to exploit a lot of properties about this data set in order to see a lot of nice features that Plotly can produce for us. Now, the first thing that we're going to create is we're going to create a scatter plot. I'm going to limit my year to just years in 1952, and I am going to compare GDP to life expectancy for all the countries in the data set. Again, this is essentially a filter function. The data set that I'm using is just being restricted to only those values from 1952. I could, of course, just use the data frame and not do this filtering function, and then I would see all of the data for all of the years that the data is available. But I just want to see what this relationship is like in 1952. And what we get is a data set that looks like this. Now, this is a little bit hard to read because the GDP per capita has this one country way out here, and then all the other countries are kind of built up on the edge. So we want to see if we can make this graph a little bit easier to look at. And so what we're going to do is we can actually modify this data set by applying a log transformation to it. Now, another thing that we can apply to this data set before we do that is we can add a third variable. We can add the size of the dots, indicate how big the population is. So that may give us some more information about how big the countries are and maybe how might that relate to their GDP and life expectancy. So again, this is still 1952 data. We're just adding this third variable. So again, now we can see these dots. And what's weird is that we knew there was a thing out here someplace, but it's so small now that it completely disappeared off of our screen. It's very hard to see that dot that was way out on the right. And we definitely still have all of our dots like clustered here at the end. So we want to try to make this graph a little bit easier to read. So one thing that we're going to do is we're going to make two modifications to our graph. of data from 1952. Again, same functions, GDP and life expectancy. Size is going to be the population, but on the x-axis, this GDP value, we're going to use the log of the GDP so that these large multiples of values, the things get spread out a little bit more. And we're going to create a maximum size for our dots so that the dots actually don't scale all the way down to teeny tiny nothing. So let's run that and see how that changes our graph. And look, this is so much easier to read. The data is more spread out because our increments are in multiples of 10, and the dots are easier to identify. We can almost see this little guy out here. And again, one of the nice things about Plotly is that it automatically has this sort of interactive property to it, in that when you're running it, you can hover over the values and it will tell you sort of the source of the information. The life expectancy here is 44, the GDP is 400, and the population is very large indeed. In 1952, I'm going to guess that this is probably China and India. Now, we can change the dates of our filter, for instance, and we can also add another variable. We can color our dots by continent. So this will help us determine what actual continent these countries are on. So that might help narrow down our understanding of which country is which of our dots. So again, I've changed the year, but otherwise all the previous information about size of the population and the log scale and the max size is still in there. And so now, again, we have a nice legend over here. We're now plotting essentially 4 variables on this graph. We have the life expectancy and the GDP, of course, but we also have the population and which continent they're on. Now, this says these are both in Asia. And again, I'm going to guess that these are China and India. In the Americas, I am definitely going to guess that this is probably the United States. That's the biggest one in purple here. These orange ones are Europe. So smaller populations, but very high GDPs. This guy out here, this is Asia. Possibly Saudi Arabia, Qatar, somebody rich. As we continue to add annotations and things like that, we'll be able to see. Oceania is very hard to see in this graph. There is Australia, perhaps, or New Zealand that is out here someplace, but most of the other Oceania countries are very small, way out in the middle of the Pacific. All right, so again, we're going to create our, we're going to continue with modifying our code so we can add some additional information. So we still have, I've changed the year to 77. We still have GDP and life expectancy. Population is the size of the dot. Color is the continent. We still have our log x is true, size max is 60. And the thing that we're adding is the hover name is country. So now when we hover over those dots, it's going to tell us, we're not guessing what country we're looking at. It's going to tell us what country we're looking at. So again, this otherwise looks the same until you hover over something. And now continent America, that is in fact the United States. This is Belgium. This is Australia. There's New Zealand. France is there. This is in fact China. This is in fact India. And this guy out here is Kuwait. Now, in this case, we're going to try to create a pie chart of our data, and I'm going to restrict the data in this example to not only the year 1982, but also the continent of Europe. So there's like 100 countries plus or minus in the world at any given point. And so that's a lot of countries to put on a pie chart. Europe already has too many countries to really put on a nice pie chart, but we're going to narrow it down so that we have a little bit more manageable information. And we're going to further tweak our data to put it in a pie chart so that we mostly are only looking at the largest countries, and we are going to put any population with a population smaller than, in this case, 50 million, we're going to put them into an other category. So that's what this is doing here. We're taking our population less than 50 million. That's what E6 is, millions. So this is 50 million. And we're going to take all of those and we're going to dump them into an other country category. And then from there, we're going to make our pie chart based on population. We're going to use the country names, and then we're going to title our graph, which we have not been adding a title before, but we're going to now add a title to our graph, the population of the European continent. Let's run this. And so here's our nice pie chart. This says that for populations over 50 million, there's only 4 countries, and everybody else, in fact, half of Europe, is composed of countries that are with populations under 50 million. Now, you can change that filter a little bit, and then you can get more or less slices in your pie. Now, the rule of thumb generally is that you don't want more than 7, give or take. It depends on, the pie slices and how well they're distributed. But you could make this insane number of slices by making the cut point like 20 million. And now we've got really way too many. Or you could just add a few more, maybe 40 million as your cutoff. And now you have 5 countries over here and then everybody else. So again, this is something that you can experiment with as you go through these examples. But this is a nice, well-labeled pie chart. It already has the percentages displayed on each of the slices. It has a nice legend. The colors are distinct and easy to read. It's not doing anything funky like perspective or anything. So this is a good pie chart graph. Now, we can also do other kinds of graphs. So in this case, we're going to do some geospatial analysis. So we're going to plot things onto a map. Maps are nice because they give us that extra perspective in terms of the locations of things. So here we're going to make the Gapminder data. We're going to turn it into a geoscatter plot. I'm going to use the year 2007. We're going to color dots by their continent. The hover names are going to list the name of the country. The size of the dots will be the population, and the kind of map we're going to plot onto is what they call a natural Earth map. And so here's our pop-up, our hover says the United States. The continent is the Americas. The population in 2007 was about 301 million. Over here in India, China, Nigeria, Europe, South America, and poor Australia down here. So again, the dots are the size of the populations, and the locations of the dots are essentially in the center of the country. Now, in this case, we're not filtering the data to be a particular year because we're going to make an animation. So we're going to plot all the years, and then we're going to run it as a movie. This is one of the fun things about Plotly. So here is our map, and here is our movie at the bottom. So here's a play, and you can also just go along the thing here, pick particular years that you want to look at. So it starts at 52. You could look at 62. You can look at 72 individually, or you can play it and watch the populations grow over time. And of course, replay it. So it's a little subtle, but it's a nice ability to be able to do. You can certainly also do this with a traditional scatter plot. If we were going back to one of these graphs, we could easily modify this to include the animation function, and then we could watch these dots move and change sizes and positions in the life expectancy GDP chart over time. Now, to do some of these more advanced ones, we're going to need to import some information about the FIPS codes that we use in the United States to indicate locations. And all of this is available on various places, including Plotly's GitHub account. So we're going to import some data. We're going to use JSON, and we're going to extract this information and then load it into pandas as eventually a CSV file. This is some unemployment data that we're going to plot. So let's read this data very carefully. So we're going to do a URL request. We're going to import the URL open function. We're going to import the JSON package. And then with this URL open function, we're going to this GitHub content for Plotly, extracting the GeoJSON counties FIPS codes as response. And then we're extracting the counties from that response. And then importing pandas, of course, we're going to read the CSV file, again, from the Plotly database GitHub account, unemployment data. And then the data type for the FIPS code, we're going to convert to a string. Again, all of these examples are from the Plotly website, and so they will have the same code there for you. So that ran successfully. So we now have our unemployment data and the FIPS codes that we need. And so we're going to create a chloropleth. Now, a chloropleth map is essentially a map that color codes the regions by, in this case, by unemployment rate. And so we're going to, and it's going to plot by county all over the United States in this case. We're going to extract from the GeoJSON file the counties. The locations are given as FIPS codes, which the counties is going to translate for us. The color will be based on the unemployment rate. We're going to use a continuous color scale, Viridi. Now, one thing to kind of mention, we've mentioned in some other videos, there are other continuous color scales that you can use. They're available on various websites, and feel free to experiment with different color codes. Oh, this is a very popular one. The color range will be from 0 to 12. There, in fact, I don't think there's any actual zeros in the database, and there might be some and unemployment rates that are slightly higher than 12, but that's basically where it's going to max out. The map box style, so that's what kind of map are we looking at? So this is the cartopositron map type. We're going to zoom in, and some of this you have to experiment with a little bit. So no zoom is basically the whole world, and so we're zooming in a little in order to look at just the United States. The center, this is essentially the center, geographic center of the continental US. Opacity, so this is just how light or dark, how intense do you want the color to be? And then the labels will be converting unemployment to unemployment rate in the legend. And then we're going to update the layout with the specified margin and then show the graph. And I'll take a moment to process. And so here is our legend. Remember, this originally in the data set is just unemp. And so we've changed that label to unemployment rate. The bright yellow are the high unemployment rates that are 12 or potentially above. So you can see some places here where the unemployment rate C is 12.1, so it's slightly higher than 12, but that's the maximum that's being plotted. And then the lowest, the darkest blues, the darkest purples are down at 0. So this is 18.6. So again, the unemployment rate goes up higher in some specific locations. 12.4. This one is 14.7, but anything above 12 is this bright yellow. And then anything that's super dark, very purpley blue, that's where the lowest unemployment rates are. So again, if we sort of look at our map, and again, this is not quite fitting on the screen because I've zoomed in a little, and so it's not fully fitting on the size of the screen with, so normally this would plot the whole country if this wasn't zoomed in so much. But you can see there's one county that is missing data, and so it's not colored at all. Other places out here, they have nice low unemployment rates, 2.5%, 2%. So again, these darker, purpler, more purpley counties are the ones with the lowest unemployment rate. So those are all, at the point where this data was collected, those are places that are in good shape, and the yellow ones are the ones where people are not doing so great. And then we can also plot other kinds of data with the same kind of information. So this is actually a voting result. So we're going to plot district locations in a particular city for one of the particular candidates. And again, we're zooming in on the city in the cartopositron type map. We're zooming into a city level rather than a country level. So this is zoom level 9. And so this is the city data. And again, each of these districts, they're color coded by the number of votes they received. Now, it's worth noting that if you're plotting by the number of votes, then districts that are larger will get more votes just by the matter of having more people living in them. And so ideally, you would want to compare these with like percentages rather than counts. But that would require some processing probably. Some information about the size of the districts. But you can see where this candidate did better. They're in yellow, where the candidate did more poorly, then they're more in that blue purple color. And in this case, we're going to modify, we're the same map, but we're going to modify the map box style from the Cartopositron to the OpenStreetMap. So there are a number of different map types that you can use as the background. And here, these are the street maps. And you can see the same information is plotted over top of the city. So it blocks out the cities, but you can see the streets around it. And then the last example that I wanted to show for this video was the 3D scatter plot. Now, scatter plots can be hard to look at. We can't plot a lot of data against each other, but we can conceivably go up to 3D. And when we go up to the 3D case, then in the Plotly, because it's interactive, we can rotate it to kind of see the graph better. Static 3D plots are not always very helpful, but when you can manipulate it and modify it, then you can get a little bit more sense of what's going on. Now, this data set actually has 4 variables in it, and so we can't actually plot all the variables in the data set, but we can plot the three of the 4 numerical variables and then impose the color for the species on it. And we're going to look at this data set later on when we do some classification. So here is the plot of our data. Again, 3-dimensional plot. We've got 3 different kinds of irises, the setosa, the versicolor, and the virginica. And again, the nice thing about this is we can rotate it. It looks like the boundary between the versicolor and the virginica is not very distinct. You can see you've got virginica and versicolor kind of overlapping each other a little bit, but the setosa has a very distinct and clear boundary between the other 2. So for classification purposes, it's going to be very easy to get a good classification of these guys down here. It's going to be much more difficult to get accurate classifications, at least in these 3 dimensions, of these other 2 types of data. So again, this is the nice thing about this is that you can move it around and you can see that sort of 3-dimensional structure because you're able to move it. Now, in the next video, we're going to talk a little bit more about missing values, imputation, and we're going to start building models, particularly analyzing correlation and regression models.